You go. All right, so I'd like to welcome you to the Division of Ecology and Evolution at the Australian National University, and I'd like to acknowledge that we are on the lands of the Ngunnawal and Ngambri people and pay respects to the elders past, present and future. And today we have a very special speaker, Martin Wikelski. I met Martin many years ago in the early 90s in Panama, where he was doing a postdoc based out of the University of Washington, looking at hormones in birds, and I'm sure many other things that I can't even remember now. Martin is a person who has multiple interests all the time. Before that, he'd done his PhD in Bielefeld, working on marine iguanas in the Galapagos. And at any point, correct me if I go wrong, Martin. After that, you headed off to Illinois for a little bit. And I have vague memories of you tracking bird migration in a car that looked like something out of a Coen Brothers movie. So that was part of Martin's movement towards tracking everything on the planet. After that, he headed off to a prestigious position at Princeton, and then returned to his native Germany, where he became director of one of the Max Planck Institute, an institute that was fairly small and slightly run down at the time, and subsequently, in collaboration with others, and notably Ian Cousins, has built up this fantastic institute down in Konstanz in the south of Germany, the Max Planck Institute for Animal Behavior, and they are doing the most fabulous work. It's full of incredibly talented researchers, and Martin is managing director. I don't know if you and Ian are but Martin's up there leading the team, and despite the size of the organization, he still manages to do research, fascinating research. And I think his story is very inspiring because it's about someone who had a vision of what they wanted to do, and against all the odds just kept driving and driving and has made it happen. Not every story ends in success, and they don't have to. It's the trying that really counts. And Martin's one of the lucky ones where all those efforts paid off. So I'm delighted to have him here, and he's a fantastic biologist, been all over the place, and will have great stories to tell us. So over to you, Martin. Thank you so much for doing this at 11 o'clock at night.
Thanks so much for the intro. It's great to see you again, and wonderful to speak to you guys. Yeah, it's actually we're still not sure if the story ends well. So because the Russians just had a leak on the International Space Station. They shut down our recording system a while ago, but in 6 days we get the turning on again. So the leaks are stuffed, and hopefully everything is working, but I'll come back to that later. But yeah, the story is not over yet. But I think the key is we want to establish what we call the Internet of Animals. And this is something that is actually started as you said in Panama and in Illinois, where we tracked animals and realized that everything is interaction. It's sort of the Humboldtian view of life, that you can really only understand systems like chemical systems or physical systems if you understand the interactions of the particles. And this is what we are trying to do with animals now. And I think this has always been part of human culture, human societies. Animals have always been really important, except maybe for the last 200 years, when during the Industrial Revolution, things turned out a little weird. Sort of everything was done by machines, and everybody relied upon machines and technology. And that's often a good thing. But then you also have warning signs. And these warning signs sometimes tell you that things are going not so well all over the place. We have those signs now. As you all know, there's a massive biodiversity crisis. And in many instances, we don't know where the problems lie, but this is where we want to track individuals and find out where these problems come from. So really the cause of this. But while doing so, I think we learned that we can really get a lot of information from animals out there as our noses, eyes, and ears in the world. And this is really also, in a way, what the sixth sense of animals is all about. Namely that you have the interaction of intelligent sensors, and that gives a new property of measurement of a system's function that gives you a novel understanding of phenomena. And I'll show that a little more detail later. Now, this is also where people always thought that animals can also be a problem. In this case, for example, in ancient Japan, catfish were supposed to cause earthquakes because they sit in these huge, and these huge catfish sit in small ponds in little towns and villages. And often before the earthquakes, they get really active and jump out of the pond. And people thought that this is causing earthquakes. But I'll also come to that. But the key about this is that people all around the world look at animals, try to interpret their behavior. We know it from our pets at home, that this is really what you can do and you can learn from them. And this is what we can now do in the Internet of Animals. But what we need there is really animals that communicate with us globally. And that is when we have these wearable computers that animals carry, then we can really understand and listen to them. And I would like to show today what we can observe and predict by doing that, and give a few examples, something like weather and climate, zoonotic diseases, now a big topic, but has been predicted to be a huge topic 15 years ago. Ecosystem services and food safety, starting to understand maybe that natural catastrophes can be anticipated locally. And then also what we can give animals in return, namely to understand what they need for survival, and that we can really care about this. Now, this is really giving animals wearables and following them around. So the first step is really more like a technical engineering step. How can we do that? And there I come to our team. We have a fantastic team who's really working on that all the time and really helping to make this happen. So a lot of very able people to really do these kind of difficult jobs, trying to create engineering solutions to these difficult problems. And that's at the University of Constance in the south west of Germany, close to the Swiss border, close to Zurich. Yeah, what we realized a few years ago was really that if you look to different scientific disciplines, they can solve big problems because they have systems to really do that. If you look at polar research, they have huge vessels. The physicists have huge rings here in Switzerland, a huge ring through the Earth to understand particles. You can look at the sky and get radio waves all around. And what we have as ecologists is really a little more than rubber boots and binoculars, but not so much more. And it's not only one telescope that the other disciplines have, they have lots, and they have lots of vessels. So it's really time that as a sort of ecological community around the world, we stand up and say, well, you know, there are biodiversity problems and we need better instruments to really solve the problems that you want us to solve. Because so far what we have done is really follow animals by hand. These are dragonflies that we followed in Illinois during migration. But at least what's nice is that we can follow all these animals, so that the basic technology is there. These are orchid bees in Panama, or monarch butterflies in Kansas. And initially, nobody believed that this is doable, but it's actually not a big deal. It's really just putting a small radio. It's almost like a little Sputnik satellite on the butterfly. And then, you need somebody who can handle it well. Then you put the tag on, and then you follow it throughout, ideally, its lifetime. And that really tells you a lot of new things that you didn't know before and you could never observe before. Now, this is now also really important because we're doing that with moths. This is with Miles Mentz, actually an Australian, who is here as a Humboldt Fellow and a Marie Curie Fellow on death head hawk moths, but you can do it on sharks. You can put on with Taylor Chappell from Stanford, who was a postdoc here. We put on a bunch of tags on the back fins of sharks to really understand how they jump out of the water. But all I want to show here is really that you can put these sensors on, and then you can really afterwards recreate, or almost in real time recreate, what these animals are doing in nature. You can do that in elephants in Southeast Asia while sitting on your computer in the US or in Europe or somewhere. You can count the trunk movements, you measure the energy expenditure, and you can really nicely calibrate that. Here, we just look at a house cat, where on the left side you see the 3D acceleration, so the acceleration in the axis of space, and you see how, in this case, it runs, it feeds, it runs, it feeds. On the right side, it's licking, and it's lying on its side. So you can see all this in very nice precision from animals anywhere on the planet now. And you just need to transmit that information back home to you, to a database where you can look at that. But you can even go further, non-invasively measure what's happening in the brain, at least to some extent. But those methods are also becoming better and better. And the good thing is that people are starting to work together on that around the world. So one of those databases, MoveBank, has set, at least in the terrestrial realm, some standards of how this can be done. And we now have, I think it's 2.5 billion locations of animals in about 7,000 studies with more than 1,000 species of animals and 25,000 users or so. So it's starting to become a community of people around the world that is really interested in these topics and can address big questions, because the papers that are coming out of that are joint papers of 150 authors. So it's going the route of the big physics collaborations. And this is really getting towards the Internet of Animals. But what we still miss is really the tracking of small animals around the world, and a global system to really do this, because the local systems with cell phone systems, or now also the IoT systems, are okay for some studies, but not for the big overarching questions. So that's why we said we want a system to do this from space, and thought that maybe prototyping it on the ISS is a good thing. But what we wanted is extremely low tag mass and size. So initially 5 gram, but going down to way under 1 gram, so that you can track the large locusts and the large insects, but at least all the small birds. But you can also track a whole number of individuals at the same time. So this is when the code division multiple access comes in. It's almost like what we had about 20 years ago, when the cell phone system switched from analog to digital, and now they are all GSM, or they're code division multiple access systems. That is now happening from ground to space in the communication around the world, that these systems are being standardized. And one of the possible standard is the Icarus standard, because that is one that is a very powerful communication tool. So we can do that globally. And there are now more payloads being built to not only have one cell phone tower in space, I mean one receiver in space, but many of them in space, so that you can have near real-time information on your animals from a lot more places. Now, being small on the ground means you have to be big in space. It's the usual thing. If you want to observe a distant galaxy, you better build a large telescope. And that's the same with these kind of communications. So this is actually the training model for the cosmonauts. This is the real antenna with the Russian space engineers helping to do the quality control. They need to be measured and checked for their properties. The cosmonauts need to train with them because they later on do spacewalks. Here's the integration in the International Space Station on the ground. So the real important stuff is behind us, but we are not allowed to take pictures because it's all classified. And then you have to go to launch it. So that means you have to, in this case, go to Baikonur and put your antenna into the rocket, and eventually, yeah, it's up there. So it sits up in the rocket, this huge antenna. The thing is being launched, and that's a pretty amazing moment. I've never expected that gravity is such a nasty thing. Then the cosmonauts have to go up there. In this case, actually, one of the rockets in between exploded, so their spacesuits were gone. They had to get replacement spacesuits, and that already takes another 6 months of waiting for your system to turn on. So everything is a little more complicated in space, but at least rapid prototyping means that a few years later, you have your system out there. So the cosmonauts spent about a 7-hour spacewalk to fix the antenna. And now here it sits. So that's a nice viewpoint down towards the globe. And the good thing is that it has already shown it's working extremely well. So the communication protocol works well. There's a downlink system, so we can command tags on the ground. There's an uplink, and there's a computer on board that deciphers all the information. And it's almost working like a vacuum cleaner going around the globe, so that the tags can sleep most of the time, which is also good. So they can be dormant. And only when the receiver comes across, then they send their data. There's a basic tag that is really just an electronics board, a battery, and a solar panel in some housing. But it's really nice because we capitalize on the consumer electronics, and we can use a lot of different sensors. So this basic tag can go on small birds. Right now, the minimum size is about a blackbird. So it's still not yet where we want it, but it's on its way at least. Or you can put it as a leg band on a large animal, or as a fish tag. As a fish tag on a anywhere in the ocean, but it has to pop up to the surface to transmit. Or an ear tag, and that's a really powerful tool to really understand the lifetime trajectories and behaviors of mammals. Or some advanced tag that has more functions. But the key is that it's at least the basic version is small, can go on something like a blackbird, and really give us information, for example, on the demise of 3 billion songbirds in North America, or 420 million songbirds that are missing from Europe. So those kind of dimensions are massive. It's about a third of the avifauna in the north that is missing. And nobody really understands exactly why they are missing and where they have gone, because it's a question of connectivity. You need to know in the breeding grounds and the migration areas and the wintering grounds what's happening to these animals. But a lot of them have now been released. The data are being collected on the tags. There's still some problems, but we had some very beautiful migrations already from Russia into Europe, and from Eastern Poland into England and so on. But a few weeks ago, the system had to be shut down because there are leaks on the ISS, as I mentioned. So this is still ongoing, it's coming, but what you can see is really the beauty of the data, because you can see exactly what they're doing, but you can also go out there and find them and observe them in the wild. And that's really the key aspect. But short of that, let's just go to what we can already do well with the kind of systems we have. So what can we observe and predict? And I think the prediction is really the important part, that we start to really not only observe what's happening, but really see that we can, from these masses of data make predictions on what animals are doing. So let's go to one of the areas of the world where this is really important, the Himalayas. This is where a lot of the weather is happening and affecting a lot of people. Bhutan, a kingdom in the Himalayas, where the State Happiness Commission is one of the most important ministries. But we wanted to study the relationship of griffins with that landscape and with people. And initially thought that these griffins, these big vultures, actually only fly around in the Himalayas. But it turns out that they go all across Southeast Asia and even up to Mongolia. So they are true migrants, at least some of them also stay. But what you then see is how dense the information is that you get. So you see that the Central Valley in Bhutan is really well traveled by these vultures. So millions and billions of points that are being produced. And what you can do from that is actually get the almost real-time trajectories of these animals, and then really see where do they thermal, how do they fly with or against the wind, how is the turbulence in these areas. And those data are starting to be fed into weather services, weather models, because those are almost like mobile weather stations that are close to the ground. And as we have seen now during the lockdown, when we don't have information from planes recording the weather forecast is actually getting much worse. So now replacing that with animals is a really good way, because they are all over the place and they are in the areas where this really matters. Now, if you go to storks circling, then that's also very nice, because they can tell you exactly where the wind blows, so the wind speed at different altitudes, and also the thermal strength. And that is a measurement that is very difficult to get in meteorology. So the animals do it for free, and they do it all the way from Europe to Africa to Southern Africa. So any place you want these measurements, just send a few birds. And that's what the marine people are already doing with elephant seals. They are among the best data gatherers in the ocean for ocean currents, salinity, temperature, and so on. But what it also gives us, and that was totally unexpected, if you look at the interactions of storks, in this case, the offspring in one entire population, in a local population, a village, the first 10 minutes they start circling together. We can actually see that here the blue ones are really rapidly ascending and then flying to the next thermal. The orange and red ones are very slow and sluggish and poor flyers. And you see on a landscape that the red ones are actually staying back in Germany or Switzerland in this case. The orange ones maximally make it to Spain, and the really good flyers make it all across the Sahara into sub-Saharan Africa. But this now also gives us a really good indication of how long-lived those animals are, because we know that if they fly across the Sahara, they will die in the first year, because right now they're all shot there. So staying in Morocco is the solution. And what's exciting for us is that through observing the interactions of these young animals in a collective setting, in a swarm, we actually gain a predictive insight into their life histories. And that's really only from 10 minutes of circling together. So that's, I think, a very exciting new aspect of behavior and high definition observations of behavior in the wild. But then you can also calibrate these systems. So in this case, we have geese that are being trained to fly next to an ultralight. They have measurement devices on their back that are as good as anything that an Airbus or a Boeing flies. And then they can actually fly next to a measurement instrument, so we can calibrate this. And this also gives nice stories for people. They like it a lot. But the key part is really that you can then go to the Arctic or anywhere where the geese are flying, and they fly almost all across the globe. You tag the geese there because they are molting in these places. So you can catch them in large numbers and really non-invasively with a neckband tag them. And then they tell you from all around the world how the wind is blowing, how turbulent it is, which direction the wind is coming from, and so on. And that's really, for a lot of these measurements, very exciting, beyond all the basic ecology, but just as a measurement, as a service, Earth exploration or Earth observation service for people. And if you look to the more detailed data, you see how many data we get from these animals. But then you can also create energy landscapes, because we can measure the heart rate of these animals. This is a bar-headed goose being measured before it starts flying from Mongolia into southern India. And then you can determine how high it flies, what kind of energy it uses, but especially for all the geese in that population, and really where they expand energy and where they gain energy. And that's, again, the factors that you need to really become predictive. But in the future, this is becoming even nicer, because we have global data, in this case on the tracks of storks, but also on the water relationships through gravity measurements from satellite. So if you look here, for example, in Chad, there has over the last 17 years been a massive increase in the water level. And this is actually now where all the storks have started to, not all, but most of the storks have started to winter from the northern populations. So they have actually really adjusted their migration routes to these long-term changes in water levels. And the details are still under investigation, but it looks very promising that there's a causal relationship there. If you look to other systems, for example, the demoiselle cranes that go from Mongolia to Beijing across the Annapurna into Pakistan to winter there, we have talked to the GRACE, the gravity people, and they said, oh, this is interesting, because that's an area between India and Pakistan where there is lots of changes in groundwater levels over the last 12, 15 years. Now, the demoiselle cranes fly in this area, but interestingly, they have a very peculiar, almost 90-degree turn that they do before they go to the coast. And we always wondered why that is happening. But if you overlay that, you see that they do this turn exactly at the place where they follow the change in groundwater over time. So again, very tempting to hypothesize that this is a causal relationship. But again, that needs to be investigated in detail. But it gives us at least a possibility to be predictive on where these animals go and why they change routes in short or medium term. So now, the second point, zoonotic diseases. It's pretty clear to everybody nowadays, but as you know, there are many, many more zoonotic diseases that are constantly emerging. So roughly 70% of these diseases are vector-borne and zoonotic. And just want to look at two, avian influenza and Ebola. So avian influenza is transmitted by mallards, wild mallards. So if you track these wild mallards, you see that they have huge migrations from a place where people just feed them on a local lake. And they always tell you that, oh yeah, you know, this duck is always here. Well, it's not, because a week later it's back in Moscow somewhere, and 2 weeks later it's back at the same place. And and people are feeding it again. But in between, it traveled almost all the way across Eurasia. And this is even more so in other species. These are pintails. So very exciting long distance movements. But what that means is that areas where these diseases are endemic, for example, in the Poyang Lake area, where you have a constant intermixing between human activity, so farm ducks and farm geese, chicken, with the water birds and wild birds and people. This is then a place where you want to look closer. And what we can do there is measure the body temperature of these ducks, in this case mallards. And we see that even low pathogenic avian influenza shows a very distinct pattern of increase in body temperature that is measurable on a population level. If you look at a bunch of animals, that is also measuring on the individual level, but at the local populations, it's very clear. And that means that you can send people there to then really sample and see what is it, which virus is it that is coming. That's something that you can't determine remotely. But what you can determine remotely is really where these animals go, because we have real-time information on water levels in these areas. And that then means that you can predict how these animals go from a place in Southeast Asia across Eurasia into other areas, and either Africa or Europe, and then affect local populations there. Or what you can also do, and that's even more telling, if you tag a Hooper swan, they are very sensitive to avian influenza. And that means as soon as they are dying, you know for sure that something is happening in that area. And they are again flying all across Eurasia, or different species in different parts of the world. So that is something where you can use sentinels to really tell you exactly what's happening. And that's even more powerful with sentinels in Africa, the flying foxes. They have a pretty bad rap because people think that they are transmitting diseases, but that evidence is actually not really there. They sometimes show antibodies against diseases such as Ebola, but they are not known to transmit it. And that's important because then it means that these animals are, for us, the best sentinels for trying to find the host of Ebola, because that's still not known where that is hiding. So you, again, just go there, you take a blood sample, swabs, you do all your good ecology, but at the same time, they can then tell you, almost like a corona tracking app, who has contact with other animals where, and where do they pick up these diseases. But at the same time, we can also study their ecosystem services, which is massive. As you can imagine, if you have a total population size of maybe 50 million, and every night they plant these trees because they transport these seeds across vast open areas, and then they are probably some of the most important seed dispersers across the African savannas and in the African forests. So local populations, for example, from Zambia, do huge migrations across the equator and come back a year later into these areas. So those are the first tracks that we have. Actually, we have some return tracks to Zambia. But if you now look at the change in greenness in Africa and look at some of those tracks, and now, and that's still a hypothetical track, you have some that then say go through certain areas of the Congo, and you know that either by sampling them afterwards or even beforehand on a population level, you can say that some of those have antibodies against certain diseases, and they are usually then located in some areas that they are either visiting in the future or have visited already, depending on whether they do regular migrations or dispersal. So by tracking them, you can then really find out where these diseases hide and narrow it down. But this is also possible in other species like camels that when there's the Hajj going on, often bring MERS, the Middle East Respiratory Syndrome, again, the coronavirus that's very deadly. And this is what FAO, Food and Agriculture Organization, knows about their travel routes. Basically nothing, just whatever some officers think they expect them to go somewhere, but nobody really knows. So again, it's not known where these diseases come from, where they hide, where they are being transmitted. And that's pretty amazing because nowadays it's fairly easy to just put an electronic ear tag in these animals and track them. So that's, I think, coming up. And nowadays everybody understands that this is an important topic. Ecosystem services or food safety, again, a huge topic, especially with the insect decline, but also the insect invasion into certain areas. And we are actually lucky in Europe that it's getting a little warmer. So the large insects from the south are coming. That's nice. So Miles Mentz is tracking them. And there it's also important that you first show that you don't hurt these animals by putting tags on. So this is a moth that is flying as normal. It's actually a tobacco moth. You see the tag is on the belly and it's doing everything a regular moth is doing. So what we can then do is really to take these moths, give them a little bit of food, in this case honey, the death head hawk moths, let them go at night, and then track them throughout the night. And in this case, it's actually nice to see during the fall migration that they are going across the Alps, they're going into the Mediterranean areas. They fly up to 400 kilometers a night, and they keep a very strong direction throughout their migrations, apparently, also over days. So we're starting to understand the kind of navigational mechanisms and flight mechanisms that these animals use in the wild and how they use a landscape. So again, that's very important once we get a better knowledge of that, because this is also what we need to really understand something like a locust swarm, because locusts are still a plague that affects lots and lots of people, 1 in 10 people around the world every year in all of these areas that you see here in brownish color. And here we can actually use another aspect of our Earth observation, guys, of the storks. And that is, we know that they are going more and more into the Chad area and also northern Sahel. And this is really also where in the last few years, the desert locusts have aggregated more and more or gained a lot more prevalence. And you probably heard that this year, last year and this year is a massive outbreak year for desert locusts. So actually the storks are or have changed their routes in a predictable way. We're still investigating that in detail to really make it as a forecast, to make it into a forecast system. But this is something where we're working with FAO and IBM to really use these data in near real time to make those kind of forecasts beyond the ecology questions that we have. And you see already that the outbreaks of desert locusts are in these areas where the storks are. So there's temporal and spatial overlap. And from the acceleration data, we also start to see that this is really where things happen, that the storks are starting to feed in these areas. And those are areas where you don't expect a lot of food, but this is where the desert locusts come off the ground. So still a lot of work to do to really validate that across these vast landscapes, but very much promise in doing that. Another aspect where there's a lot of promise and a lot of research potential, but it's very frustrating because it's very hard to study natural catastrophes. people have always, oh, and we patented that recently because we're trying to get industry interested in that, something like the reinsurance industry, to use these kind of applications and then have the revenue to support people in these areas to really understand their own animals and use their own information from these animals. But there's lots of information from even the old Greek philosophers that animals can predict earthquakes. Humboldt had some observations during his trip to the New World 250 years ago. Whether that's true or not, we don't know, but at least what we can do is track them and find out, so get real data. We tried to do that in areas like Banda Aceh, where there was the huge tsunami, but obviously that's retrospectively not the place to try to do that, because if you have an earthquake or a tsunami in some areas, then it's very unlikely that another few years later or so you have another one. But it's really impressive what happens during these times. I mean, it's horrific what happens. So the earth basically shakes or floods or everything's destroyed. But at least in Banda Aceh, some of the elephants survived. So we tried to understand, well, have those elephants got special skills to understand what's happening? But again, it doesn't really make a difference because, or it didn't give us the data because there was no other tsunami, thankfully. But then we thought, let's go to a place where maybe the natural catastrophe is a little more benign, but at least more often. And that's volcanoes that are not exploding, but just spewing some lava, like Mount Etna in Sicily. And sometimes it's actually at least very annoying and threatening to animals and people. And there is a huge lava being thrown out. But what we think we could do, or thought we could do at the time, was really to tag animals all around the mountain and see how they change their behavior in anticipation of something that's happening there. And that's very interesting because initially I thought we track wild animals like deer or foxes, but then we talked to the local herders, the local farmers, and they said, no, take the goats. The goats are really good. They are very sensitive. So we tracked the goats, and then also had their acceleration pattern being recorded all the time. And that's really interesting because if you look at the regular nights, so the stipple line, you see that there's always a little bit of activity going on throughout the night. But there are some nights when this activity is really jumping up, and you can either do it by threshold or you can do it by first principle models. It doesn't really matter much. The good thing is about 4 to 6 hours ahead of a major volcanic eruption, you will see changes, massive changes in the behavior of these animals around the mountain. And if you do it not just in one local group, but in many groups, then you know that this cannot be a fox or a wolf trying to eat these animals, but it's really a long-term disturbance, a fear response that is very powerful, and that seems to be coming up before these volcanic eruptions. Now, this is something I mentioned earlier, that we are starting to understand what people always call the sixth sense of animals, which is, I think, nothing but what we starting to understand in collective behavior, that if you have sensor swarms like what we have in the cell phones in cars, if you have lots of them interacting, then you can actually predict how long it will take to work, or how long, where the traffic jam is, and what other routes are there. So those kind of things are really what I think is happening when animals interact. They learn from each other, and we can learn from them, and gain a deep understanding into phenomena that we didn't even know we want to know. I mean, Google traffic, we didn't know 10, 15 years ago that this would be possible, or maybe 20 years ago, and now everybody is using it. So I think these sensor swarm ideas and emergent properties of these sensor swarms are very powerful. We also tested that with earthquakes, and there it's even more difficult because you need to find an area where there's an earthquake before it happens, and that's obviously the holy grail, so that's too difficult. But what we did was in the end to have tags ready and say, well, if there's an earthquake, we just had to rush there and at least understand how the aftershocks are being perceived. But the good thing was that we had an earthquake in Italy. We went there, which is also a little difficult that you don't go there and ask people whether we can help them. You also want to do that, but you also want to tag their animals. So it's a little weird in the beginning, but there are a lot of people who are interested in that because they know that their animals tell them. So they want to know from us, well, give us means to ask our animals, give us means to learn from our animals continuously. And here we went to a farm by chance that was actually within a larger earthquake area where 15,000 earthquakes happened, some large, some small. But we had actually some that were right below the farm. And interestingly, you see that there are earthquakes before a massive earthquake is happening. So these are aftershocks. The blue lines is the acceleration behavior of these swarms of farm animals here. So you see that there's a lot of variability, but that's something that we can easily sort out because it's depending on daytime and several other factors. But importantly, it is also always increasing before major earthquakes in the area. So within about 20 kilometers. And that's being analyzed on first principles, just as if you compare stock market values. So we actually did two analyses levels. One was really just a first principle, just compare time series, and we see some very strong effect, but there's a lot of noise. But if we then go in and say, well, with our knowledge of animals, if these animals are super active, like twice as active as normal for 45 minutes at a time, so they don't calm down, they're really there's mayhem on this farm for 45 minutes. If we make that a threshold, a biological threshold, then we actually see that we get a fairly good predictability of the earthquake and also even the distance of the future earthquakes from these farms. And that's nice because it means that we could set up a triangulation system when you have different farms with different animals being tracked, then that could give you a good indication of when and even where locally an earthquake, a future earthquake can happen. So within about 2 to 10 or 15 hours. And that's important because, as you know, these earthquakes in these areas are massive. Here you see that one side of the mountain was sliding off against the other, about 1.5 meters or so, 2 meters. And we are doing that right now in seismic hazard areas. So right now we have a real-time system down in Chiloé in Chile. Same system we have in Italy. And they give us these data now every 3 minutes. And we can hopefully see whether we can be better in our warning times and warning systems than other systems that are out there. This has been criticized by seismologists. That's good because so far we only have one earthquake series in one area of the world. So it's obviously not enough to really show that this is a good system. But we are fairly convinced that we see data that are really allow us to forecast these earthquake systems locally. So these are the data from Chiloé, where we see what's happening in real time. But then I think what's really important is to give back to the animals, and that's a really important aspect in the Intergovernmental Panel for Biodiversity and Ecosystem Services in IPBES, in the the Global Biodiversity Panel. So how can we know what's happening to these animals? And I think that's, again, really exciting that we can finally track individuals. Here, again, one of the graphs showing 420 birds missing from Europe. But for many people, if you tell them, then they say, well, you know, I don't really care. Why should I care about 420 million birds missing? I don't know them. But if you make them individuals, if people, kids, everybody just knows, oh, this is my animal, my pet that has flown into a net and is being eaten now, or it is my orang that is now being released again into the wild, because we can track it, we can observe it, we can protect it. That makes a totally different story. And for the orangs, that's really important because there are lots in these rehabilitation centers that are waiting to be released, but people don't want to if you can't protect them out there. But you can also then track animals that are protecting other animals, because you can learn their behavior. Here, a cheetah with an electronic ear tag, you can learn their behavior and then see if there are poachers in an area, for example. So if you want to protect rhinos, you have to track all the plains game, the giraffes, the zebras, the antelopes around these animals, and to then know beforehand that a poacher is coming. And then you also know where the rhino is through your tag, and then you can finally protect it. So this is actually something that we are building up in South Africa now with Kruger National Park and South African National Park Service, to have IoT, Internet of Things, tags, systems in animals such as the lions. Here you see one with an electronic ear tag, or the rhinos that are carrying these solar ear tags now. But they are, again, then being protected by the animals around, and you ideally take the lighthouses. You don't need necklaces or neck bands anymore, because you just put these ear tags in, these ear tags that can be in small animals and grow with the animals. So you learn the entire ontogeny and life history of these animals, but you also use these data at the same time to protect other animals. But then this can also be done, for example, in fish. You can't transmit from out of the water, but you in these eels, for example, if you want to know where they go, you put a tag with a skin sitting tag, and then pop up the tag eventually, and then you know what happened to these animals in between. Or a parrot in here between Guatemala, Mexico, and Belize, because they are the umbrella species that allow these establishments of multinational parks, multi-country national parks. Or in peregrine falcon that are being hunted for, that they can be trained for sports hunting. Many of those go from the high Arctic into the southern continents. But again, there is a problem because a lot of them are being hunted in between. In the Galapagos, that is being done to understand how tortoises, for example, interact with goats or invasive species. So again, you learn about their annual migrations, but at the same time, you can protect them and guide them throughout their dangerous periods in their lives, or do that for reintroductions, like in the buffaloes, where initially, obviously, they are just restricted to some large farms, but eventually they are out there and interacting in a real landscape. This can also then help you really understand interactions, like in this case, the griffins that I showed you for weather forecasting, how they interact with people, how this intricate relationship has really persisted over decades or hundreds of years. In this case, how the griffins actually eat dead people there. So through the sky burials, our griffins eat about 25% people. So the chain of nutrients is actually pretty complete in these areas in Western China, Inner Mongolia, and Tibet, and also Bhutan. But it was interesting for us to see that even nowadays you have systems where this is really sort of intact. But the important part is that we engage people in these observations. This is important from a science perspective because we want to understand what animals are doing in places where we can't observe them all the time. But people are always there in these areas. So if a swarm of tagged animals arrive, so even single tagged animals arrive, then people can go out there, observe them, really gain information, and also gain a personal relationship with these animals. So that's possible with the animal tracker. I think there are about 180 species on the animal tracker now, total several thousand animals. And you can really go out there and see what these animals doing. You can follow individuals and really then even on a lake like in our area, find the ducks that were only a week ago in St. Petersburg in Russia and are now back and are being fed by people on the lake. But it also allows the kids to be part of that as a group. So in school settings or in university settings, in museum settings. And that is what we call the sessilization of conservation, because you can go from sessile a lion, from this idea that you have one tagged animal that has been shot, to really then help individual animals. You make them special. And in this case, for example, we're tracking the ontogeny of migration in demoiselle cranes. And these young cranes that you see here are later on getting leg bands during their ontogeny. So we know exactly where they were born, what they're doing. But then they can be followed in different populations. So you learn about the migration culture, but then you also learn about the individual problems that they have. And these are mostly problems during migration where they are being hunted or being shot, artificial lakes being built. And the nice thing is that if you have people that care about these individuals, then if these individuals are being hunted, are being shot, often they show up somewhere. And for example, here, demoiselle cranes do show up also on social media. And this is where you get the information. And this one crane that I showed you beforehand, this young crane that was later on tagged as a juvenile and then was shot, actually changed the legislation for these birds in Pakistan. And more than any of the 420 million birds that are missing, this one crane then really made a big impact through the action of these people that cared for these animals for conservation of cranes. So I think we are actually very close to establishing this Internet of Animals. There's lots of information we can get from that, from the interaction of these animals, from global syntheses, for example, the Arctic Animal Movement Archive, or now the Anthropause, so the change of movement of animals throughout the time when fewer people in many places of the world are out in natural areas. So this is giving us a unique way to study the interaction of animals in nature with humans during these times. And it's almost like sitting on top of your goose, like Niels Holgersson, and flying with your goose and really understanding what these animals are doing in the wild while roaming the planet. They give you information on what's happening on the globe, on natural disasters. They help protect the place. And I think we can protect them and have a deep understanding of biology and a prediction of individual life histories. So thanks a lot, and I hope I have some questions about it.
Fantastic. Thank you, Martin. I know how strange it is to be talking to yourself in a room late at night. So, but you had many people listening there, and that was absolutely fascinating. And there's so many different elements to the work. So I'm going to have to run off very soon. So we've got about 5 minutes or so. If anyone would like to ask a question, can you please raise your hand, and I will then turn on your microphone and allow you to ask Martin a question. So don't be shy. If you want to ask a question, raise your hand. Here we go. We've got one from Megan.
Hang on. Okay, that was fantastic. Thank you. I was just wondering what kind of resolution you can get with this tracking. Like a lot of the stuff you're talking about is over hundreds of kilometers and stuff. But like kind of what's the smallest resolution you can get?
Smallest we're getting now is 1 Hertz GPS. So 1 GPS point every second. And at the same time, you can get, say, 100 Hertz resolution in your acceleration. But usually you can't do that throughout the day because you don't have enough energy. But we just tagged a bunch of vultures in Cuba where there's good light. And we now already have about 2 million GPS points from them. So it's actually accumulating rapidly.
So what is that in kind of distance wise, like meters?
Or? In distance, that's I mean less than meters. Yeah, that's
wow.
Really
it's amazing. Thank you.
Sure. Thanks, Megan. Martin, I'm going to have to hand over to my colleague Dan Noble, who will then handle people asking questions, and I'm sure he can operate this. And when it's finished, if you just press the stop recording and then end it, and it'll record. Martin, thank you so much on behalf of everyone, and we'll let you take as many questions as you can handle. It is after midnight, Dan.
Yeah,
so.
I know.
All right, and I'll send you an email thanking you afterwards.
Okay. Yeah, thanks so much.
Lovely to see you, Martin. Bye. Take care.
Yeah.
Hey, Martin. It's not often you get a text message saying, please come to my office right now, thinking, shit, I'm in trouble. Are there any other questions by anybody? Oh, sorry. Megan, can I... no one else? I don't see.
There's one question about the units of code activity. Those are actually it's OTBA, so overall dynamic body acceleration. It's the sum of the vectorial sum of the acceleration in different axes. So it's a measure of a correlate of animal energy expenditure.
Oh, we have 2 more questions. Margarita, I'll allow you to talk. Oh, are you?
Hi, can you hear me?
Yes, we can.
Hi, thanks Martin for the talk, that was wonderful. I would like to know, because the title of the talk was actually the Internet of Animals. And I was wondering if you have maybe explored the possibility of using animals as communication nodes. So not just, following the Internet of Things concept.
Yes, so that may eventually work. We have done that already, or tested that, so that some animals collect the information of others, but it's actually in most cases, from an energy point of view, not really efficient, because they have to, the receivers have to listen too long for other radios to talk, and that is energetically not very feasible. But for us, the sort of the Internet of Animal idea is more that you then, I mean, either in real time or almost real time, you connect the information in the real internet, but the information, the movement and behavior information from these animals, and through that connection you can actually learn about the interaction. So I think that is in most cases more efficient, because the mechanical receiver, so a regular radio receiver, than to each other, just from energetic points of view.
Okay, thanks.
So, we might just take one more question and then let Martin go, because it's quite late there. How about Brett? Looks like you have a question.
Hi, thanks for a really interesting talk. My question was on the availability of all of the monumental amount of data that you're generating off the back of this. Is it all open data, or parts of it open, or is it possible to access this and analyze it, like sort of genome bank or something like that?
That's exactly the idea. I mean, there are some restrictions because you have some animals that you have to protect, and you can't make those data completely public, say from a rhino or the breeding site of an endangered animal or so. But in general, it's going that direction. So all of our data are public as we get them. So for example, if you want to look at MoveBank and see what the vultures in Cuba are doing, we just tagged them a month and a bit ago, and everything is open. You can look at these data and analyze it. I think the key is that we want to go this route of these large-scale collaborations, because in the near future, the problem will not be to gather the data, but really to analyze them and analyze them in a large-scale consortium. So there is still a human sociology component that some people are very restrictive on their data, and they are very sort of reluctant to share, but it's starting to go that route, that people are more and more willing to share and collaborate.
Thanks, that sounds great. There's certainly plenty of tools out there which could be applied to this sort of data.
Oh, sorry, I didn't understand.
There's the sort of tools that are being applied to using machine learning and some of the network analysis tools that are out there now. It seems like perfect kind of things that you could try and direct into this sort of data.
Yes, exactly. And we set up a system. It's called the Move apps. Just went online a week or two ago, where it's actually people can write R code and scripts, but then we can actually wrap them in ways that everybody can use it. So even if you can't program, you can then click the program of your favorite programmer and say, I want these data of mine or somebody else's data, and I want to filter them in this way, and then apply the program that this person wrote, because that's super cool and really helps me understand my data. So it's really almost like a high-level analysis and programming that now everybody can do on these animal movement and behavior data.
Thank you very much.
We might leave it there because we're already well over time, but thanks for everybody who came. I think there were about 65 people that showed up at the end, Martin, which is a great turnout. And thanks very much, as Mike said, for giving us a talk. It was a fantastic talk and really cool to see what has been going on up there. And I'll stop the recording now.